Okay, a few preamble remarks. I updated or Grace kindly updated the notes. A few typos and minor corrections. If you want to download, they're in the same places as before under the first lecture, I think. Also, I don't, I guess I want to announce some positions we have. It will sound like a lot, and I don't want to make it to sound like bragging, and they're all not mine. But so the first one is mine. So I'm currently advertising for a postdoc. So if you know any good people, we'll let them know. That closes 16th of August. Our school in Sydney, School of Maths, UNSW Sydney. So they are, I think around mid-August, they're going to open 2 positions, continuing positions specifically for dynamical systems. One more theoretical, one more applied, or computational. And then maybe a month later or a few weeks later, we're going to have 6 more continuing positions in the school, 2 for pure, 2 for applied, 2 for systems. So there's a lot of positions that maybe you can mention to your contacts. So yesterday we started to talk about stability of the spectrum. And I had the preamble saying what kind of information were you interested in. It could be something like in the deterministic case, you take your map and you perturb it to some nearby map, or you apply some noise to a stochastic system, which effectively makes a new transfer operator, or you apply some numerical estimate method to estimate the transfer operator. So all of these produce some perturbed operator that I'm calling L epsilon, and epsilon is the size of the noise. Okay, so I think I already set up this triple norm. So now I go to the assumptions. There's 3 fairly straightforward assumptions, and then I give the theorem. So first, you want that for all epsilon close to 0, that the weak norm of the operator is what's called power bounded, meaning that you can have an R here. If this were a Frobenius operator, you could just choose the R to be 1. So this is not very, R can be bigger than 1 here, so this is rather mild, I would say. Then you need the Sodiork inequalities of the type we've been talking about. And the only real restriction here, which is not much of a restriction in practice, is that the same constants here should hold for all the epsilon. But again, as we'll discuss, if your L epsilon is coming from, say, Ulam or convolution with a kernel, then you can usually use the same constants you had for your original transfer operator. And then you need to say that these the perturbed and the unperturbed are close. And so we use the triple norm to say they're close. So this triple norm distance should go to 0 as epsilon goes to 0. So all in all, fairly mild conditions from a dynamical kind of setting. So let's look at some examples of things that satisfy this. Let's say L epsilon is the Ulam approximation on subintervals of width epsilon. So what I have in mind is you pick n subintervals and they have width, say, floor 1 epsilon. And then what you do with Ulam is you project onto, we discussed this before, you project onto this span of indicators on the subintervals. And the L epsilon is L. Oh, I'm mixing notation here, sorry. So, but I think you know what I mean. So you take the true L and then you project. And okay, note that because this pi n, it was just doing conditional expectations on subintervals. So let's say, I don't have too much space here. Let's say I draw the graph of some f. I'm going to apply pi n to, and these are my subintervals. Then pi n apply to F, we'll take the conditional expectation on each subinterval, and you get this step-like approximation. So now if you think about what happens to the Lasserre-York inequality, if we're in BV, then this norm is made up of the variation and the L1 norm. And by doing this procedure, I, if anything, reduce the variation. I certainly don't increase it. And I also don't increase the L1 norm. So for Ulam, you can just take the same thing here, and you can take the same thing here. For any epsilon, you don't need to change the inequality at all. Similar thing happens if you, so I guess in summary, if you're in this setting, if you're in this quasi-compact setting where you have a Lasserre-York inequality for your map and you apply Ulam, you're going to be good. You might take your transfer operator and convolve it with some stochastic kernel. So just to be concrete, let's say we have a kernel that has a uniform density on minus epsilon epsilon. So the way you would interpret this dynamically is you have your point, you iterate t, and then you smear by convolving with your kernel. You smear on an equal minus epsilon epsilon from t of x. And then you iterate again. Then you iterate that smeared. Then now you're not iterating points anymore. Now you're iterating densities because you've already smeared. So you iterate you push the density with the true operator and you smear again, and so on, so on, so on. So this is like adding IID noise, where you anneal the noise at every discrete step. And I think you might believe me if I say this process is variation reducing. And because we're convolving with a density with a stochastic kernel density, I don't increase the L1 norm. So again, I don't have to do anything to these constants here. And yeah, I can choose this to be 1, just like in the Ulam case. I guess what I haven't addressed is the closeness. So for Ulam, what that would mean is the triple norm, essentially the triple norm of the identity subtract pi n goes to 0. And no, that's not too hard to show. That's actually a classical result from analysis. And with the stochastic kernels, yeah, this is also not too difficult to show. So both these situations are very easy to verify the conditions. Okay, so now the statement. It looks a little long, but I tried to be careful here. So let's say what it's going to say is that if you have a true eigenvalue of your true operator, then if epsilon is small enough, then you're guaranteed to find an approximate eigenvalue nearby and with the right multiplicity. So let's see, I'm trying to draw a picture here. So this is the complex plane. And you can think of, in the Prof case, think of this as being the number 1. The R here, you can think of being R essential of L. And you just pick some R prime, some radius R prime that's larger than the essential spectral radius. So here's your essential spectrum disk. This is 1, or your R, and you pick something here or here, and these are the true ones. And then what you do is you say, okay, I look at all points here, union the eigenvalues I get from my perturbed operator, and I intersect that with a little delta ball of a chosen lambda. So I choose a lambda. Let's say I choose the one with the red circle around it. So this is a little delta ball. And what the theorem says is that, yeah, for epsilon delta small enough, then the intersection of the eigenvalues that I get from L epsilon, maybe I do those in green, so there would be maybe a green one here. So this thing here is an element of the spectrum of L epsilon. Inside this ball, you get just eigenvalues of your L epsilon, and as epsilon goes to 0, these go to the true eigenvalue, and the total multiplicity is equal to the multiplicity of lambda. So it might be, of course, that maybe this cross here has multiplicity 2, and I might get 2 separate observed ones, but they all coalesce, and the total multiplicity will match.
Sorry, Gary, I'm a little bit puzzled. I mean, if delta is small enough, then surely the delta ball wouldn't intersect the set of set with mod set less than or equal to R anyway.
Yes.
So why is that even in there?
Yes, I see your point. I mean, it's not an incorrect statement. You're just saying.
Yeah, it's a correct statement. I'm just saying. Simpler.
I guess it slightly extends the range at which delta could be, but if you don't care about that, then I agree it's redundant. Yeah. Okay, so that's for the eigenvalues. Now for the eigenspaces. In the usual way, we'll have, so you have these spectral projection operators onto the eigenspaces of your observed operator. So I've written this explicitly here. So you do this integral around this is big enough to read all the subscripts, around the delta ball of your lambda, like in my picture. So this is going to project onto the eigenspace associated with lambda epsilon. Oh, well, the total eigenspace, the direct sum of the eigenspaces associated with my 2 green dots here. And you do a similar thing for L. And then the result is that, I mean, there's something here about rate, but the main message is that the triple norm distance between this projection operator and this projection operator goes to 0. And for sufficiently small epsilon and delta, the ranks of the operators which are finite will match. Okay, so that is pretty much what you could ask for. Yeah, I'm just summarizing here, I guess. So if you're in the situation where you have the power boundedness and so the organ inequality, so you're in this, and you have compact embedding, so you're quasi-compact, you could view this as all you really need is then the triple norm convergence of your perturbed operator to your true one, and then you get all the convergence you want. In particular, the fixed points of your approximate operator converge to the fixed point of the true one, and which would be the invariant density, and similarly for the other isolated eigenvalues and eigenfunctions. Okay, now I want to do this in the random setting, and the end results will be a little more modest. Mostly I'll concentrate on the top oscillated space, which corresponds to the random invariant density. Okay, so same setup as we have all the time. We have a collection of maps. We concatenate according to the driving sigma. If we're in this nice situation from before, from these results, then we have a unique random invariant density, this collection phi omega 1, and these transform like this. You take the density at time omega, you hit with L omega, and you transform to phi sigma omega. Now what I want to do is subject each L omega to its own perturbation. So for every omega, I perturb the L omega according to, for example, the 3 ways we talked about. I might perturb in my map co-cycle. I might perturb each map, or I might convolve with a stochastic kernel, and that kernel can also change from fiber to fiber. Or I might apply Ulam on each fiber, or a mix of these. I mean, it doesn't really matter. All that's going to matter in the end is that you have this triple norm closeness on each fiber. So you might on one fiber do a numerical estimate, and on another fiber change the map, if you wish. Okay, and what we would like to know is that, well, what this will produce is, I don't know if I wrote this anyway, but this will produce a co-cycle for L epsilon. Say here to produce. I'm going to change the notation, unfortunately, anyway. But, so you have, for each omega, you have your L omega epsilon. Now you have your co-cycle of these guys under the same driving. And what you would like to know first up is that at least this has a unique random invariant density with an epsilon here. And then further, you'd like to know, as epsilon goes to 0, do these fiber-wise converge to the true one? So now you have, if I say omega is this way, maybe omega is sort of time like this. And on each of these omega fibers, I have some estimate, let's say, of some perturbed invariant density on each fiber. And what I'm going to do is let epsilon go to 0 on each fiber. And on each fiber, I check, do the phis match? Does the limit as epsilon goes to 0 match the true thing on each separate fiber? So it's a very strong type of convergence. It's for almost every omega, I get this convergence. As I noted here, this is very different to sort of convergence in expectation over the omegas. That's much weaker. Yeah.
Is it unreasonable for the driving to be perturbed? So not the maps, but the driving?
Yes, it's a good question. I think there's probably, probably some work on that. It makes it, I guess, a little, obviously more complicated and a little less comparable. But yeah, in principle, one could do this, and there may be models that would fit. Yeah, but I'm not looking. I guess the reason is because I'm trying to keep the assumptions on the driving as minimal as possible. So all I'm assuming is just ergodic and inverse, which is like super general. So any stochastic process you could represent this way. And right. Now, sorry, I'm changing notation here. So what I did previously call L epsilon, I'm now calling LK, just for technical reasons that I have a discrete sequence that I'm going to travel along. So the idea is as k goes to infinity, epsilon goes to 0. Here I have some basic measurability conditions. I want the omega and x dependence to be measurable so I can do things. Also for the perturbations. And so now I go through some hypotheses. And so this is joint work with Cecilia from 12 years ago or so. So first we have the usual condition we had before when we established quasi-compactness. This is about essentially the growth rate of the maximum growth rate along orbits of your co-cycle being finite. We asked simply the same thing. I just put a k here. Okay, so it's the same as what we asked before. I just asked that the same thing holds for all my perturbed co-cycles. Also, because this is going to be concerned with approximation of invariant densities, I want the perturbed operators to be positive operators. So they map non-negative functions to non-negative functions. And I want them to be Markov, so they preserve Lebesgue integrals. And if your perturbation is a stochastic kernel, well, if it's any of the things I said, actually, if it's you perturb the map, then you get another transfer operator, which is Markov. If you convolve with stochastic kernel, you get, again, a Markov operator. If you apply Ulam or some numerical, actually not apply Ulam, you get these properties, you get a Markov operator. All right. Then we also need some Lasserre-York inequalities for the perturbations. So it looks essentially the same. Don't worry about this condition. This is a technical condition that lets me make this random. So that's it. Yeah, that's not the main game. The main thing is that previously we had something like this. So that was not there. And we just had what was the BV norm of L omega F in terms of the BV norm of F and the 1 norm of F. Even in the random case, right? Before I started talking about perturbations, this is what we had. Now I have to control also all the LK omega F BV norms. But I can control them in the same way. I just ask they satisfy the same kind of Lasserre-York inequality. And having these coefficients random is a big help. really expands the class that you can treat. Okay, third condition is that we want the co-cycles to be close, the perturbed and the unperturbed. And the way we ask this is pretty mild, I would say. So what we ask is, maybe this is the simpler one to look at, their equivalent. I just write it explicitly here, the triple norm. So you want the triple norm distance. You look at all omega, you fix a delta. You fix a delta, you ask, what's the likelihood that my triple norm distance is bigger than delta? And as k goes to infinity, you want that to go to 0. So this is convergence in measure, which is a kind of mild, very mild sort of, I'm not asking for almost every omega that this happens. Okay. All right. And then the final one is just to say that the unperturbed co-cycle has a unique random ACIM. And this is also phrased in this convergence in measure language. So you take some mean 0 function under iteration of the co-cycle, you expect this to converge to 0 because you've taken out the invariant density part. And what we ask is that if you pull back n steps, you push forward n steps, the one norm being bigger than delta, this likelihood should go to 0, or as long as you push sufficiently much. So more specifically, if you fix some probability threshold and norm threshold, you can find an n depending on those. So if you iterate sufficiently, you get that. Okay, then the result is that I think I've already said all of this so far. So the result then is that R, the unperturbed one, has a unique random invariant density. And if your k is large enough, so too does your perturbed co-cycle. So we'll call that collection phi omega 1k. And then now for fiber-wise, for p, almost every omega, you fix the omega, you look at the convergence with k, and this limit goes to the correct object in L1. So that's good news. And the types of perturbations, again, they can be all the types that we've been discussing. Perturbations of the map, convolution with kernels, or numerical methods like Ulam. There's one little postscript I want to say. So maybe you say, well, maybe this requirement here is a bit too strong to get in one step. Although notice, as I mentioned yesterday, this is on average, right? So you could be composing 2x mod 1 and 1/10 x. And as long as you don't apply the 1/10 x too much, then you're good. So there's still some flexibility. However, you still need this in one step. And if you're wanting to apply Ulam, it's what you could do is choose an n naught, a little n naught. So you iterate your co-cycle long enough until for one step of that n naught co-cycle, this is true. But that's a bit practically painful because you don't want to apply Ulam to some high iterate of your map co-cycle. But it turns out that it's not necessary. So this is it's a follow-up work with Cecilia as well and Will Murray. So what you can show is under the same conditions, if you're so specific to Ulam, if you are in a situation where you're only eventually expanding on average, so that means you would have to choose some little n naught in order to satisfy the condition, you can still just do the Ulam projection for each individual map and it all works out fine. You get the same convergence result. So this is practically very nice. Okay, and I'm going to end with, I'll say a little bit more about these random invariant densities. So we already discussed that you can think of phi omega 1 as you take some arbitrary density. Yes?
Sorry, do you mind explaining again the condition you want on your previous the meaning of it?
Yeah, it's kind of, I mean, it's like a, you cannot, it's a weak form of convergence to zero, essentially. I mean, the way we apply it in the proof is you say, okay, assume you have like an F1 and let's say you have two random invariant densities. You have like an F1 and F2, and then you can take the difference, and the difference would be in V0, and this condition turns out to be what we require. So maybe it doesn't look the most natural, but it was weak, and we like the weakness of it. I mean, I guess you could assume stronger things than this that maybe appear a little more natural. I don't know, Cecilia, if you want to add.
Yeah, I think what you said, though, it's a weak condition. Yeah, but
It's necessary.
so something is.
We didn't want to have an omega-wise condition. So like the previous one about the triple norm distance, we like this convergency measure, and this is kind of mimicking that.
So you want kind of some contraction to be happening more or less at the same time for the different omegas, right? So some control across omega, but without having uniformity or something like that.
Okay. Yeah, so we saw earlier that you could interpret phi omega 1 as you pick some arbitrary density in the past, n steps in the past, you push it forward to now, and you, in the large n limit, that arbitrary density would equilibrate this. So now, here's another way of phrasing things. Let's say you have some observation function on your domain, and you make some random Birkhoff averages like this in the usual way. So you pick an initial condition in your phase space, you iterate your random orbits, and along the random orbits you evaluate f. So you get this bunch of random numbers, and you take the Birkhoff average. Okay, so using the ergodicity of the driving and the fact that we have mixing in the co-cycle, what you have is a Birkhoff on the skew product. So you can show that this, what I just described, is equal to the integral over omega cross x. That's where the skew product lives. The phi d Lebesgue is your fiber measures on the phase space, and here you average over your driving space, and you're averaging f. So this is time average equals space average. And now you can say, well, all right, so now I apply Fubini and I interchange the two integrations. And I'm able to do this because the f doesn't depend on omega in my example. I mean, you could also have an f depending on omega, but here for what I want to say, it will not. And then what you're doing here is creating it's called a phi 1 bar. So you're taking all the phi 1 omegas on each fiber and you average them to make a phi 1 bar. Okay, so how can you interpret this phi 1 bar? So let's say your f were an indicator on some subset of the phase space. Then what I'm doing here is counting the asymptotic frequency that I land in A for the random orbit. Over here, what I'm saying is, well, that asymptotic frequency is, I would be integrating over the indicator of A. So I'm taking the phi 1 bar measure of A. So phi 1 bar is telling me how random, if you were to make a histogram of the random orbits, what would the histogram look like? It would look like phi 1 bar. So phi 1 bar is sometimes called the physical invariant measure for the random dynamical system. Because if you don't know what the omega happens to be or which realization you're on, and you just look at the distribution of points in your orbit, in the long run, they all turned out to be the same, and they're distributed according to phi 1 bar. And in general, to get this phi 1 bar, you need all the phi 1 omegas. So this leads me to the next point I want to make. What you could do, and what has been done, I mean, it's a very old idea, is you might think, oh, well, to get this phi1 bar, what I'll do is just take my transfer operators and average them over omega. And then I have some lovely single operator, and I just compute it I hope it has a unique fixed point, and I just compute the fixed point, and you get something interesting. And so you might wonder, okay, does this, let's call this phi1 hat, the thing I get from this average. So does this have any dynamic meaning, and is it equal to the phi1 bar? And in general, the answers are no and no. The exception is if sigma is Bernoulli. If sigma is Bernoulli, then it makes sense to do this. So, for example, to take something concrete, let's say your omega is this infinite product we discussed a lecture or two ago. So we're going to do IOD noise, IOD epsilon noise. Sigma is the left shift. And so this would model additive noise applied to a fixed map. So you could define your T omega to be some fixed T plus omega naught, where omega naught is the 0th component in this bi-infinite product. So in this case, the answers are yes and yes. So does phi1 hat have a dynamic meaning? Yes, and it is equal to phi1 bar. But in the non-Bernoulli driving case, I don't know of any dynamic meaning of the fixed point of the averaged operator. Okay, and to illustrate this, so this was a few years ago, but I think, if I recall correctly, I think what we had here were random beta maps. So the domain is 0, 1. I have so the map, so T omega X is beta omega, that's correct, beta omega X 1, 1. And then the driving, I think the driving was a irrational circle rotation on omega. So sigma omega equals omega plus some alpha 1, 1. Alpha not rational. And we did 3 things. So one is we ran a very long orbit and we made a histogram, and that's shown in the dashed dot line. The next thing we did is we applied the previous result, this one, so we did Ulam on each fiber, and we computed for many omega the phi omega 1s, and then we excuse me, and then we averaged them to make this phi1 bar, and that is the solid blue line, and the solid blue line and the histogram are mostly pretty well overlapping, which is what you would expect because phi1 bar is meant to represent this histogram. And then in red, sorry, I don't know what's wrong with my voice. Then in red, we did we formed the L bar from the same large number of omega, and we computed the fixed point. And what you get is the red line. So this illustrates, of course, the driving here. I mean, this is not too unexpected.
Want some water?
I have tea here.
Okay, good. Sorry.
To be superior to yeah, this is expected based on what I said earlier, because I said in the Bernoulli case in the non-Bernoulli case they should be different. And well, this is very non-Bernoulli. But it shows that these so-called annealed operators, they give you statistics and invariant densities that can be very different to reality, what the random orbits show. So this is a cautionary tale, if you're not aware of it. Yes.
Wait, for an engineer, the annealed version looks better in that it captures the general trend without the
Yeah, I could also put a smoothing. I could I could progress a smooth fit if I wanted.
I see.
But I see your point. Yeah, if you want something smooth, I guess. Well, this is one example. I mean, I did not exhaustively explore all the L bars, but I guess it makes sense that they should be somehow smoother than the true. But I think you want something that represents the true statistics of the random system. Otherwise, I mean, it's just something like smooth but different. To smooth but not representing what's happening to the trajectories. I agree, it's not completely crazy, like it's not.
Yeah.
But okay, and right. So I've talked about stability of the leading oscillated space. I mean, in this invariant density language. So we previously had this E1 of omega, which is spanned, my notation, spanned by these phi omega ones I've been talking about. Okay, so now you might ask, what about the E omega 2, 3, and so on? They're the cases, the situation is not so, yeah. So I only wrote one little paragraph on this. There is, so either, so one thing you can do is make stronger assumptions on the original cocycle. So if you assume that the original transfer operator cocycle is uniformly hyperbolic as an operator cocycle, then there's a, so Eric Crimmins has this random version of Caloy-Liverani that will give you the same kind of results. So there's triple norm convergence and convergence of the Lyapunov exponents. Or if you want to assume less about the original cocycle, then you have to be a bit more specific about the noise or about the perturbations. So one thing that's been shown, again, this is joint work with Cecilia, is that if you have your original cocycle, and if you perturb with IOD noise, and the noise should really be smooth, let's say, should have a density, then you get some positive stability results. But this relies on the smoothness and the independence of the noise. There are many counterexamples where if you choose, you can choose pathological perturbations and things will go wrong. And Cecilia with Antiquas has done, I mean, another approach is if you want to talk about transfer operators, you can also think about specific classes of systems for which you can prove some positive and negative results about stability. And Cecilia is the expert on that. Well, that's the end of my first part, so maybe I can call for questions, otherwise I'll go to my second part. So I split these into two chapters because in chapter 1, everything I talked about is Heron-Frobenius operators. And in chapter 2, we're going to talk about transfer operators that are not necessarily, they're like slight modifications that are very handy, but they're not Heron-Frobenius operators. So to start, I'll look at some statistical limit laws for dynamics. So let's say we have, back in the deterministic setting now, we have our map T. Let's say it has this unique, absolutely continuous invariant measure. I'm calling this mu, but mu has density phi1. So phi1 is d mu d Lebesgue. This should sit in our Banach space, which you can think of as BV. And let's say we're in this quasi-compact setting we've been discussing. So now what I do is I choose some observable G. So this is some real valued function on your domain. It should be in the Banach space and it should be essentially bounded. And with this, we can now define a stochastic process as follows. So ZK is your stochastic process. And what we can do is just say, well, it's constructed by, you make observations of G at, along the orbit, essentially. So these are all functions. You think of your domain. Now I'm thinking of I think of these as random variables. And what is the usual omega that the probabilist would think of? So the probabilist's omega is my, say, unit interval. So I would pick a point. I would randomly pick according to mu. I would randomly pick according to mu some point in 0, 1, and I would evaluate my random variable on that point and get a number. So you think of these as random variables, and they are stationary with respect to mu because of the composition of T. Now you can define a mean for this process. That will be the expectation of G, which is just integration with mu. So we'll call it G bar. And this is going to immediately disappear because I'm going to assume that I subtract the mean. Simple, keep the formula simple. So there's nothing, so without loss of generality, I will subtract the mean. There's nothing important about keeping the mean. Okay, so the first thing I want to look at is the central limit theorem. And yes, I'll go through a few lines and then I'll show you a movie. So how would you normally define the central limit theorem? You would sum up your ZKs and you'd scale from say 1 to n, and then you'd scale by 1 root n. So this is exactly what we're doing here. We make now what is a Birkhoff sum, but I'm really summing my random variable ZK, and then I scale by root n. So it's like a deterministic version of the usual central limit theorem. And if your dynamics is chaotic enough, one reason the central limit theorem works is that you have the independence. And in chaotic systems, if you measure observations along an orbit and they're temporally separated enough, they will be almost independent by chaos, by the hyperbolicity of your system. So this is why the central limit theorem works in the deterministic chaotic case. So this will converge in distribution to a normal. The normal will have mean 0 because I subtracted the mean, but it will have some variance remaining. And the variance is given by this expression here. So if this looks slightly weird, it's compatible with the usual sort of variance. So let's say you had a sum of dependent random variables xk, each with mean 0. Then what would be the variance of this sum? Because of the mean 0, you can write it as just the expectation of the square of the sum of the random variables. And this is exactly what we're doing here. The reason for the n here is because the root n gets squared. But otherwise, you're just plugging this expression here into this. So it's completely compatible. Okay, so I will show you now a movie for people who like to see movies. This is really fancy because it's 2D, not 1D. So this is on the left, this is the two torus. So I have the cat map, the usual Arnold 2111 cat map on the two torus. And on the right, I'm plotting a histogram of this Birkhoff sum scaled by root n. The convergence to the normal is in distribution. So to illustrate this, I'm going to begin with an ensemble of initial conditions, and that initial ensemble is uniformly distributed in the square. And then I start iterating all the points, the entire ensemble, into the future. And as I do that, I update the histogram here. So I think it's probably not possible for me to actually pull it back to the very first frame. Oh, it is great. Okay, so I have some G, which I can't exactly remember what it is, but anyway, it's not constant because you can see that the histogram is taking values in a range, say on this square from -2 up to whatever, -1.3 or something. Okay, so there's some variation of the values on this square. And then as I run a little bit like here, okay, now what I've done is it looks like I've taken 3 steps, 3 iterations. So this went to this, went to this. So n is now 3. And I've computed the Birkhoff sum for these points, and the histogram is evolving. And then as this goes, it will converge to something that looks like a normal. pretty quickly. Okay, so this is one way to illustrate the central limit theorem. And there's nothing particularly there's nothing special about how I chose the observation or the initial ensemble. And also you can see that the mean is not quite mean is about 0. And there's some variance. And the variance is what I want to discuss computing. Okay. But I see that I'm out of time, so I think that may be a good point to stop. Thanks. Okay. Thank you. Yeah. Thank you for trying to get rid of me earlier. No. Okay, so great. I have another 15 minutes. Sorry. Good your hopes on. Very fast. Okay. So that's intro to central limit theorem. I have another movie, don't worry. So now I want to talk about large deviations, which is related but different. So now if we have some positive variance, you can construct what is called a rate function. So what you're doing here is, so down here, I guess I don't know if this was a good idea, but I suppressed the x notation. So what I'm doing is picking some threshold s, let's say positive, like 0.1, and I'm computing these Birkhoff averages of my g. Now my g has mean 0, so I would expect by Birkhoff that if n gets large, then this Birkhoff sum should get close to the 0 function, because that's the mean. And so it will get harder and harder to pick initial conditions x, so that this Birkhoff sum with large n still exceeds something non-zero, something positive. And the set of initial conditions that are bad, that have these large deviations, so the being larger than s is the large deviation, the set of initial conditions will shrink exponentially quickly in n. And I want to know the rate of that exponential shrinkage. So to get that rate, what I do is I take the mu measure of the set of initial conditions, take the log and 1 over n and take the limit. And for each, that gives me a number, which is the rate. And then what I can do is I can vary s. And it turns out that you get a rather well-behaved real-valued function of s. So in particular, this rate function is, so it's non-negative, because I put a minus sign here. So this rate itself will be negative, but then I put a minus sign, so it's non-negative. This is a continuous function of s. It's strictly convex and has a unique minimum of 0. So qualitatively, it looks like this. Wait, this is s, and this is r sub g of s. And now, yes.
Sorry.
Yes.
There's a question.
Because it just says there exists an open interval, do we know like how big that interval can be or how restrictive this is?
Yeah, I can give you a silly. So, okay, the silly answer is it can't be, s can't be larger than the maximum of g. But you will need to show this, you need to differentiate and you can, let me see. I don't know quantitatively if it's so easy to estimate, but you know, often in these proofs, you have there exists an interval. So quantitatively in practice, it might be difficult to get that.
And what specifically goes wrong if that interval is like outside? If the interval is small and you go outside the interval, whether like does the continuity break? If they're not well defined, what do you lose?
Yeah, good question. I don't know if you. No, maybe there's not a problem. I don't know. Sorry.
It may be infinity, right?
Right.
So this thing.
Can it get infinity before you reach the maximum of g? Is it? I'm not sure if it's possible. You would have to somehow shrink super exponentially for thresholds below the maximum of g. That would be like.
Yeah, it may be the maximum that's seen by the measure or something, but you can get infinity if you're not in French. So I think that's what we want to avoid.
If you numerically try to extend out, then what you'll see is that this will diverge to infinity, and I guess in the experiments I've done, the G is always fully supported, and okay, that's a good question. I'll try and chase that up so I have an answer next lecture. Maybe yes. Okay, so if you like to visualize these things, back to the beginning. So again, it's the two torus and the cat map. I think again, I'll shrink this back to the very first iterative. So what was my observation G? I think it was something like involving sines and cosines in 2D. So something like an egg carton sort of contour that maybe holds 4 eggs. And on the left, what I'm showing in blue is the bad set, the set where your Birkhoff sums, your Birkhoff averages exceed the threshold. So here I chose a particular S, which doesn't matter, it's some S. And the blue is the bad set. And then on the right, I'm plotting versus n, the orbit length, the log of the measure of the bad set. And what you expect for exponential decay is that this is a straight line. And also you expect that this will get small exponentially fast, which it does, but then you sort of hit a pixel limit and it looks like it's not getting any smaller. But on the right, if you measure it, then you get this straight line down to 10 or 12 or so. So this is how, in this example, this is how the bad set would evolve and look. Now, in the deterministic case, the nice thing is that these quantities, the variance and the rate function, you can get from derivatives of a modified transfer operator. So this is called a twisted operator. So what you do is you define a new operator, L sub z, using the usual Heron-Frobenius operator, but you pre-multiply by e to the zg. So z is a complex number, g is your observation. So f is a function of your domain, real valued, so too is g. So this makes sense. So the theory I'm going to describe, you can see this in, there's a book by Henny and Hervé that is good, and Quizel has a nice survey. And there are many nice things. Okay, so one nice thing is that as long as, if you start with the quasi-compact L, if your twist is small enough, you remain quasi-compact. This is a kind of super nice modification because exponential was super nice, the function of z. So this is a much nicer perturbation than the types of perturbations we were talking about before with Keller-Liverani. Yes, so Lz remains quasi-compact if the z is close to 0. Of course, notice if the twist were 0, you just get back your original Heron-Frobenius operator. And also the leading eigenvalue of Lz, which I'll notate like this. So lambda is the leading eigenvalue. It becomes a function of z. The corresponding eigenfunction becomes a function of z. And these are differentiable in z because of the analytic form of the exponential. And you can Taylor expand the lambda in z about 0, and it looks as follows. So, okay, let me explain why there's no constant term. So there's no constant term because lambda of 0 is that's 1. That's 0 twist. You've got your Heron-Frobenius operator, so your leading eigenvalue is 1. And if this was just 0th order, I would put in a 0 here. I would get e to the 0. That would give me 1. Okay, so the constant order term is 0. Why the linear order is not there, z, is because I subtracted the mean on my g. It's not so obvious. It takes a little work to see that, but that's the reason it's not there. And so what you're left with is this quadratic term. And then it's a nice little exercise, a couple of lines to show that if you differentiate twice and evaluate at 0, all you end up doing is just pulling out this constant here. So this, in principle, gives you a nice way to get the variance. All you have to do is compute the second derivative of this twisted operator, second derivative of the leading eigenvalue of this twisted operator at 0 twist. For the rate function, you again use this leading twisted operator, and you again use the differentiability, and now you have to do something slightly more complicated. You have to, for reasons that would take too long to explain, but they're in the nice references that I gave you earlier in this survey, in this book. You have to take the convex conjugate of log lambda z. And it turns out that this rate function is the convex conjugate of log lambda z, which is by definition what I've written here. So if you've done some optimization, you might have come across convex conjugates. There's an optimization built into this because you have to take the supremum of your twist over the range, the valid range. Yeah, again, if you wanted to do this numerically, this is possible. It's just a one-dimensional line search. And this is a very nice expression as well, even though it looks a little odd. Okay, so if you, I guess I'm not developing in detail the theory for the central limit theorem and the large deviation principle. I want to talk about make you think about stability of these things to perturbations. So let's say you have your map and your quasi-compact, and you know you satisfy a central limit theorem, and you know you satisfy a large deviation principle. Suppose now you perturb your system some way. Then does the variance change in a continuous or differentiable way with the perturbation? How does the rate function change with the perturbation? Do you get something completely different or something nearby? So yes, let us, the remaining few minutes, look at that. So what you can do is consider perturbations of the type we're always looking at. We could perturb the map, we could convolve with a stochastic kernel, or we could apply a numerical scheme. The difference now is that we have these twists. So applying Caludrani is not immediate. You have to do some work to show that you have two limits going on here. You're taking the derivative with respect to z, which is some limit involving z going to 0. And you also have the perturbation limit. And you have to make sure that these work nicely together. But you can do that. And some of these papers, this was done. And what they show is that you can still exploit the Caludrani theorem with no additional hypotheses. So nothing further needs to be assumed to prove stability of the variance and stability of the rate function in C0. And I might get through this. Okay, so I'm not going to show the rate function. This is a little more complicated, but for the variance, there are various expressions to express the variance and various expressions to express the second derivative of the twisted top eigenvalue at 0. Here is one of them, and this one is nice for computation, at least, because it does not involve any derivatives. The derivatives are always a little nasty with computation. People who have done linear response might recognize this term here as being the derivative of the invariant density. So one way to, what we're going to do numerically is we have an Ulam estimate of L. As a leading eigenvector of the Ulam estimate, we get the invariant density phi1. We have a discrete representation of the G, and we can put all these things together to get an estimate of this derivative. And here I will, I guess, finish with this code here. So to run this code, you have to run the previous code. So let's say this is for the map. Remember, T of x is pi x mod 1, and the L here we think we're acting on dv. So that we define our observation. Let me just do this bigger. Let me just remind you what everything looked like, the setup. So this is what we did last time. This was the graph of our map. This was the Ulam matrix. This was our numerical spectrum with the central spectrum bound, which was 1 on pi. And this was the invariant density. So now I'm running orbits, I'm running long orbits. Those long orbits are going to be distributed according to this invariant density. And I want to compute for this observation function. I just chose something kind of nasty because we're in BV, so why not, right? So, okay, you don't have a derivative here, but who cares? And you have a discontinuity here, but who cares? It has finite variation. So this is my observation. So as I run my orbit, which is distributed like this, I'm sampling outputs according to this function. So I generate a long sequence of real numbers, and I want to know what is the variance in my central limit theorem corresponding to those numbers. And actually, I don't know if it's so exciting to see the number, but maybe I just instead run through this. So we define, again, we have 200 of these subintervals. I just pick the midpoints. X is the vector of midpoints of the intervals. Here I subtract off the mean of my observation G. And then what I would like to do is solve this. The problem is that this only exists on mean zero functions, but it's going to be okay because this has mean zero. Numerically, to enforce this, we have to solve a little linear system that enforces that the solution is orthogonal to the one function. Okay, so we set up a little equation here. So we have not the resolvent, but just I minus L. This term here is what I'm applying to. So this is just this. I think it's almost exactly the same. And then this in a product condition here, this is these ones. So I'm just summing up. Yeah, I'm just approximating this Lebesgue in a product by these ones, and they're multiplied by the solution to give zero. So that zero is this zero here. And then I just solve with least squares using backslash. And then once you have all the ingredients, I'm just plugging everything together. I'm using the formula here. So this formula is, almost symbol for symbol, this formula here. And that gives me my lambda double prime. So if I run the whole thing, then I get a number. So my variance is about 0.093. All right, sorry, I went a bit over time. Now I'm stopping.